Right. Welcome everybody to this edition of the ICTS Think Seminar series. Today we have in-house ICTS person. We have Chandramouli Chowdhury, who's a grad student here at ICTS, and he's going to talk to us about his recent work on determining a physical protocol for detection in quantum gravity. So over to you, Chandramouli.
Right. Okay. First of all, thank you very much for giving me this opportunity. As you see, my title is a physical protocol for detection in quantum gravity, but it's and all of it is going to be based on this particular paper, which we wrote last month with Olga and Subrat. So let me start. So this particular work is building on mainly these set of 4 papers and some work by other people, but it's mostly these 4 papers. The first one is especially relevant for this talk. Although everything that I'm going to talk about would be in ADS, but if someone wanted to see how things worked out in flat space and how you can actually understand the notion of holography in flat space, this is an excellent paper to look at. And there's also some older work by Subrat and other collaborators on the subject. So, okay. So in the first part of the talk, I'll try to give a brief overview of the entire setup and also, the main punchline of the talk. Then I'll try to share some more details on everything in section 2. And in section 3, I'll try to just finalize the entire argument. The main chunk of the argument will be completed in 1, but section 3 will finalize some more stuff. Section 4 will give a complementary way of looking at it. Then I'll conclude in section 5. And 6, 7, 8 are mostly some more technical / messy details, which if people are interested in, we can look into afterwards. Okay, right. So the main takeaway from this talk is the following thing. Like in ADS, we are all used to the fact that all information is encoded on the boundary in a single time slice. This is going to give us a notion of holography. We're mostly familiar with the statement from area CFT. And that typically builds on some sort of string theory and some particular background. But in this particular talk, I'm not going to be making any reference to string theory or even ADS-CFT as such. Everything that I'm going to say will be just based on some basic expectations from a theory of quantum gravity. Okay. Like I said, everything in this talk and also the paper which it's based on is going to deal with global ADS. And I will not be talking about flat space or anything in this talk. And what we want to get to is the following statement. Let's say you consider global ADS, which all of you know is like a box. And then you'll have a set of observers who are living close to the boundary. And the observers are all in a single small time band. Okay, this is essentially a small time slice, or it's a single time slice, but with a slight width. But therefore it becomes a small time band. And the idea is that they'll make some simple measurements in order to determine what excitation is inside ADS. So if you consider empty global ADS and you try to make some excitations on top of it, then observers who are living on the boundary in a single time band will have to determine what that state, what that excited state is. And all of it, and mostly the state is going to be denoted by G or something like G modified, and I'll describe that later. So as we are in global ADS, there's a unique vacuum state. And the fact there's a unique vacuum state can be seen from some simple effective theory calculations. This, that ADS is like a box, and you can quantize things on top of it, and you end up getting some discrete energy eigenstates. And the lowest one, which we can set to having 0 energy, is what I'll be calling the vacuum state. Okay, so there's no degeneracy in the vacuum or anything in this setting. Okay. Okay. Like I said,
can you explain your point that there is no degeneracy in the vacuum in this setup again?
Oh, so all I'm saying is that if you, this is equivalent to thinking of a particle in a box. in quantum mechanics, you know. In quantum mechanics, if you just think of a particle in a box, then you can quantize the energies and get various energy levels, right? So there you have a ground state and then first excited state and so on and so forth. This is very similar to that.
Maybe we need to redefine what we mean by effective theory to define the vacuum state. Because quantum field theory, there can be degenerate vacuum states, and I think we are working in the setup similar to a QFT.
Yes. So by effective field theory, that's what you mean, right? You just mean some typical old QFT and curve space-time like setting, where you just take a quantum field and quantize it on top of ADS.
In QFT, there are degenerate states, degenerate vacuum.
Sorry, excuse me. I'm really sorry, Shrant. Maybe we should. This is like just a very simple thing. If you take QFT in a box, you know, you'll get a unique vacuum. There's no. I mean, it's a simple thing. But maybe, you know, if we let him continue his talk, we can come back to this later. But what he's saying is just, you know, you just take a quantum field theory, put Dirichlet boundary conditions in a box, you will find this.
Okay.
But yeah, thank you.
Okay. All right. Okay. Thank you. So maybe I'll proceed now, and you can ask me if that's not clear towards the end. Okay. So the energies will actually be quantized in units of inverse of LADS. This LADS denotes the ADS length scale, and we'll have discrete energy eigenstates. And what we will be mostly concerned will be with measuring the energy of a given state. So as I said, we'll have some set of observers on the boundary, and the thing that they'll mostly be concerned about will be to just measure the energy of the given state. And this measurement of the energy will be done in a quantum mechanical sense. And that is explained in the points below. So this just means that the Hamiltonian of the theory will be treated as a quantum operator. So you can write down the Hamiltonian in this form. P of E are the projectors to some particular energy eigenstates. And this way of writing it just means that you have an equation of this form, that H acting on any particular energy eigenstate just gives you the energy eigenvalue of that energy eigenstate. Now, in other words, what it means is that if I perform the measurement 1,000 times, then all 1,000 times I need not get the same answer. In a classical setting, I'll always get the same answer, but in a quantum mechanical setting, I'll not necessarily get the same answer always. Now, of course, these all of these measurements will be done for a low energy eigenstate, and that will become, and I'll make that point a little precise in the setup, but this is the main, or kind of the basic idea. And in here, as I said, we'll be measuring the energy of the state G, and we'll be mostly, and then we'll ask the following question. So let's say the observers measure the energy of the state G, and then they check the frequency with which they get the value E. Okay, E is some particular energy eigenvalue. This E could even be 0. Then that would basically ask if the state is a vacuum state or not. This will also become clear in the next slide. And one thing that I will be assuming in here is that Bond rule will apply to measurements of this kind. Okay, and the Bond rule is just the following statement, that the frequency with respect to it, the frequency with which you get E is equivalent to measuring an object of this kind. Okay. So how do we know if the state is a vacuum state? This can easily be done by measuring the energy of the state G and seeing the frequency with which you get 0. Let's say you perform 1,000 measurements, and out of that 999 times you get 0, then it means that it's almost certain that G is the vacuum state. Okay, but of course the vacuum state might be a very trivial example. You could have had more complicated states, and let's say the next simplest state you can think of is some typical excitation about a vacuum state. So let's say you wanted to check if G was equal to some excitation on top of the vacuum state. And throughout the talk, I'll be using this notation many times, that X acting on 0 will often be denoted as ket X. Now, in case the observers want to check this particular thing, we'll have to give them some more powers. By some more powers, I mean, along with measuring the energy of the state, they'll be allowed to make some simple manipulations of the state. And then they're allowed to perform measurements of energy on top of that. So the kind of manipulation that they're allowed to do is that they're allowed to act with simple unitaries on the state. Okay, so they can act with unitaries of the following form, where J is some perturbation parameter and X is some operator localized near the boundary. This has to be the case because the observers are themselves localized near the boundary. Therefore, they can take the state G and get some state G modified out of it, which will look which would be something of this form. Okay. In the next slide, we'll show how the observers can correctly determine if the state G is indeed equal to this or not. Okay. The claim is that such a measurement would enable you to tell if the state G is coinciding with the state X or not. And by such a measurement, I mean they just have to compute the expectation value of P naught in the state G mod. The state G mod is defined as the unitary acting on the state G, like I defined previously. And this can be seen as follows. It's a simple calculation. In here, the assumption that will be crucial for me right now will be that the state G itself has no overlap with the vacuum state. I will make this point very precise later on, but as of now, this is going to be an assumption. So if you just take this quantity and just plug it here, I could have put J squared terms, but I'll tell you in a moment why that doesn't matter. So notice that if you just take this expression and expand it out, this is a very simple expansion, and you look at the first three terms, in all terms, you'll have a term of this kind. And in all the three terms, you'll have a term of this kind, which is just going to give you 0. Okay. Therefore, the first non-zero term that you will get will be of this kind. And you could, and then of course you could expect higher order corrections, but we'll only be interested to in order J square of this particular quantity. Now, why did I say that if I put the J square correction here, that won't matter? That's because if you have a J square X square term in here, then you'll again end up getting something similar to the order J term. That is, you'll get something like minus J square by 2 G X P0 G kind of an expression. And again, those will become 0. So the only contribution that you can expect from there is at order JQ. Therefore, that will be a subleading term. Okay. So therefore, if you take the state G mod and then ask the question as to how many, and then measure the energy of that, and then ask how many times you get 0, this is going to tell you if the state G is coinciding with the excited state X or not. Okay. Now, here I've only chosen one particular X. Notice that I was asking if G is equal to one particular X acting on the vacuum or not. But in general, if you consider a set of possible operators on the boundary, like you can consider many such X's on the boundary, which are, then the idea is that they'll form a basis by themselves. What I mean by this is that you can take any state on let's say the full time slice of ADS, and you can represent that exactly in terms of small x's, in terms of x's acting at a single time slice on the vacuum. Okay, this is something that also happens in local QFT. By this I mean that if you just take some just take a scalar field setting, and you let's say you're on the Earth and you act with some operators in the vacuum state on Earth, then you can in principle create any state on the nearby galaxy. Okay, and this has nothing to do with non-locality or non-causality or anything of that sort. It's only a property of the fact that the ground state in QFT is an entangled state, and I will say a lot more about this in the final slide of setup. So as of now, the only thing that you need to take away from this is that I can consider many X's on the boundary and they'll form a basis by themselves. Therefore, if the state G was something more complicated than just a single X acting on the vacuum, but let's say the G's were something like summation over Ci Xi, then by this logic, I can determine if I can determine the value of mod of the expectation of mod of the overlap of G with X for all the basis states. Okay.
Hi Chandra, I have a question.
Yeah.
So far I'm trying to understand this. Like so far, whatever you're saying is how we usually think of measurement and so on in some quantum mechanical system.
Right.
But usually when you say, okay, I can do an experiment 100 times or something, and then check the probability of how many times you get a particular value, you have the freedom to prepare the same quantum state 100 times because you're preparing it. But when you say it in the context of some cosmological observation like this, how do you do the experiment you said? Say, check if it's projecting the vacuum 1,000 times, because I don't have the freedom to create the cosmological state 1,000 times, right?
Right. Great. Good. Okay. Thanks for the question. I should have mentioned this before. So, of course, this is not really exactly the same as cosmology, right? In cosmology, the experiment has already happened once. And in order to set up something in ADS, you might want to set it up in a lab. And by lab, I mean you might want to simulate ADS in a lab. But, something like, so what I'm really imagining is there's some sort of a big global ADS. And in that, you've got chunks of smaller global EDSs present on the boundary, something of that sort. But, asking a question like this is kind of true in any kind of question you ask about entanglement in curved space-time. Let's say any kind of measurement of entanglement you want to talk about in curved space-time, you have to think of some setup like this. So I don't know if you can set it up in real life right now, but the best probably you can do is set it up in some computer simulation.
So Akhil, just to add to that, Akhil, the thing is that any quantum information question you ask, you have to have this, right? If you don't have multiple identically prepared states, you can't make any sense of asking quantum information questions at all.
Yeah, sure.
Okay. Great. Okay, thank you. So maybe let me proceed. Right. So now let me tell you why this kind of thing will only work in gravity and not work in QFT. Because something like, this kind of a statement is also like something like 0.3 is also present in the QFT. So why is it that something like this will only work in gravity? Now, the reason why it only works in gravity is because in local quantum field theory, you've got microcausality. What I mean by microcausality is that operators in space-like separation commute. Okay, so if you take a point which is on the boundary, and you consider a point which is deep inside the bulk, by point I mean you consider operators in those points. So an operator which is deep inside the boundary will commute with an operator which is and an operator which is inside the bulk will commute with an operator which is on the boundary. Okay, and in here what I mean is, let's say I've told you that you can make measurements of this kind, that you take some G, you act on it with some unitary, and then you measure the value of some projector. It can be any other projector, of course, like any projector which is completely localized on the boundary alone. And notice that something like this would be equal to something like this, where in the second, where on the second case, I'm considering some U bulk, which is an unitary in the bulk acting on the state G. And you consider an expectation value of this kind, U bulk will commute through all of these values and will go and hit this and just give you the left-hand side. So therefore, distinguishing G versus U bulk acting on G is impossible in a local QFT. Now, this should alone convince you that something like this is not possible, like something, what I've said previously, is not possible to do in a local QFT. But you can also have so many other formal statements. One thing, for example, is that a state with no energy in quantum gravity will tell you that you're in the vacuum state. Okay, but a state with no charge will not tell you that you're in the vacuum state. This has to do with the fact that in gravity you cannot have negative masses. In here you can just have a charge Q and minus Q placed in vacuum, which is an excitation on the top of vacuum, but a projector onto a sector with zero charge will not be able to tell you that there's something like Q and minus Q existing. Okay. Then of course there are no local gauge invariant operators in gravity. That's because in gravity, the moment I put an operator somewhere inside the bulk, I have to specify its coordinates, and then I can always think of a diffeomorphism acting on it, which also actually prevents split states in existing in gravity. But okay, I won't be talking a lot about split states. It's just a very formal statement which just tells you that if you have two operators which are in space-like separation inside some special state eta, then they just factorize in this form. They just split in this form. So this x prime could be located somewhere on the boundary, and this x could be located somewhere inside the bulk. So anyway, so given that split states can exist in QFT, you can always hide information.
Here
Yeah.
you have on the left hand side you have some excited state, and on the right hand side it's the vacuum state.
Yeah, so this is a very formal object, as I said. I mean, it's something which you can define in the QFT, but it's the explicit construction of this is usually very hard, and as far as I know, it can only be done in scalar fields till now. But yeah, this is how I'm defining the state.
Okay.
Okay, so yeah. Before I move to setup, if there are more questions from overview, I can take them now, or
Yeah, I just want to clarify. So this project, isn't it hard to find projectors which are just in the boundary projectors in say QFT?
Yeah. So right. Good. So in QFT, of course, this projector need not be like let's say you consider a scalar QFT. Then of course the projector need not be localized. I'm just saying, in case you could find a projector which is localized on the boundary. Let's say you're in QED, for example. Then you could consider something like the charge operator. And since the total charge operator you can determine by the electric field on the boundary, by the Gauss law, then you can think of projecting onto sectors of 0 charge or -1 charge or something like that.
Okay, thanks. Yeah.
Okay. All right. So if there are no more questions from overview, let me proceed to the setup. Right. So this thing I've already mentioned that I'll just work in global ADS. This is going to be the metric. The explicit form of the metric won't really be very important for me, but just to state what it is. And point 2 is something also which I've already stressed before, that the low energy Hilbert space can be obtained by quantizing dynamical fields, and there exists a unique vacuum for this particular metric. And this is something that you can easily see from a semi-classical computation. Now, as I said, we'll only be interested for states, the states G, which have relatively low energy. By low energy, I mean that if you decompose them into some energy eigenstate basis, then only the states which have E less than some lambda would contribute. It can have some E greater than lambda. It can have some overlap with some E greater than lambda, but that won't. Those coefficients will mostly be assumed to be close to 0. Okay. Then everything that I'm going to say in this talk will be for a pure state. You could ask what happens for black holes and other stuff, but I'll discuss a little more of that in conclusions, but I'm not going to say a lot about black holes. Okay, then the observers who are going to measure the state G, they have to kind of get a rough estimate of the state G, which should kind of coincide with the true state G with some accuracy delta. So this delta will be up to me. So this delta will also specify the number of measurements that the observers can actually make. They can make 100 measurements, 1,000 measurements, or something like that. And that will control things like delta. But yeah, this delta won't really appear, but all I want to emphasize is that as long as this tolerance is permitted, we are good. We don't really need to get 1 all the time. Okay. Right, now just to repeat, the kind of allowed manipulations that we have, that the observers can add some Hermitian operator to the Hamiltonian. This will lead to the action of some unitaries on the state, which is of this form. And this J is a perturbation parameter, so I can think of some expansion like this. They'll get some modified state by acting on the state G with some unitary, which would just look like this. And then they'll be measuring the energy of the state G mod. Okay. Now, if you want to think diagrammatically, then you can imagine this to be global ADS. And this red strip is the small time band in which the observers are located. And the observers will only be making measurements through this time band. And you will need observers which are spread across the whole of ADS, because the energy or / the Hamiltonian is an operator which is itself spread on the whole of ADS. Okay. So in this particular gauge called the Pfeffer-Graham gauge, where you actually set some fluctuations of the R component to 0, like H, R, mu to 0, then you can show that the Hamiltonian in the Hamiltonian of the theory takes this particular form. H00 is just the metric fluctuation along the 0, 0 direction. And because this is integrated over the whole solid angle, you would need observers spread across the whole solid angle to get a complete measurement of energy. One can of course ask what happens if the observers are not allowed to measure, are not given access to the whole of ADS, but only a part of ADS, then yeah, we don't exactly know how to make this protocol work right now. But yeah, there are some expectations and we can discuss about them later. But as of now, I'll need observers which are spread across the whole boundary. Okay. Now some points of caution. We cannot perform something similar in classical GR. Okay, because in classical GR, of course, due to things like Birkhoff's theorem and some other variations and some other variations of that, you can always think of the total mass being conserved at infinity, but you know, the state inside you can always smear in some way you want to. And notice that there's really no violation of causality. Just because I'm telling you that all information is present on this particular time band or this particular small time slice does not mean that causality is violated, because observers in the end have to really meet up at a particular point and sum the results. And that will obviously take more time than light crossing time, because an observer at the opposite end has to coincide with somebody on you know, the front end. So this will take more than the light crossing time. So in reality, if the observers have to meet up and then discuss the results, then it will cross light crossing time. But in principle, all information is located on a single time slice. Okay. And in here, the observers are themselves a part of the system making the measurement. It's not that the observers are decoupled from the system. It's not like, you know, the observers are in some other system where there's no quantum gravity or something. The observers are themselves a part of the system, but we are assuming that their back reaction is low enough to not create any high energy excitation. Okay. Now, as promised, this fact that X acting on 0, by X I mean some boundary operator acting on 0, is going to form a basis, is only using the entanglement of the state and has nothing to do with violation of locality. Okay. This is something you can also see in a simple 2-qubit system. In a 2-qubit system, of course, the Hilbert space is very simple. So in there, you can consider some generic entangled state, which is, say, of this form. Here, A and B denote 2 subsystems. And I take any generic entangled state of this form, and all I am allowed to do is act on psi with operators corresponding to A. Something like I can act with 1 plus sigma 3 in the A basis. And all I want to do is I want to create the complete basis for the bigger system. So I can act with some operators and end up getting 1, 0, 0, 1, and say the same state with the minus sign. So that will make sure that I get the basis for the big system by only acting on operators with, by only acting on a particular subsystem. So this is only going to use the fact that the state is entangled, and is never going to use the fact that you're violating locality or anything of that sort. Okay. Now, before going to the protocol, if someone has any questions about the setup, I can take them now. Okay, so if there are no questions, maybe we can go to the protocol. Right. So if you remember, then I said that I'll be considering states which don't have an overlap with vacuum. But if this is not the case, and in most scenarios this won't be the case, then what I can do is I can act on the state G with a unitary. Again, the unitary is going to be localized near the boundary. That will give us some state G prime, such that the overlap of G prime with the vacuum is 0. Okay. Then using the protocol, which I'll describe below in more detail, I can recover G prime. And then I can reconstruct G by acting with the inverse of unitary. So we have an explicit construction in the paper of how you can construct the unitary, but if someone wants to hear about it right now, we can discuss it after the conclusion. It's in the section called orthogonal unitaries. Okay. Now, the protocol will be a set of steps, a series of steps, which you would do in order to recover the state G. So the first thing that you can do is you can act on it with a unitary of this kind, which we've discussed already twice by now. And you can explicitly compute the energy, you can compute the energy of the state, and you'll get something of this form. This will fix the expectation value of G in a complete basis of state X up to the phase Gx. So notice that I'll be getting the mod square of this value. I won't really be getting the exact phase. But if I want to get the exact phase, I'll do that now. Okay. Now for getting the phases, we need to find just two low energy operators XR and XI. And in reality, we just need to find one low energy operator XR, and we can find XI from that. But anyway, in case you're able to find two low energy operators XR and XI, which have this following property, that the overlap of G with XR is just a real number, and the overlap of G with XI is an imaginary number, then the claim is that you can exactly fix the phases. Okay, so the first step is to play with this guy. So what I do is I take an unitary of this form. So this is just e power I j xr plus x, and I act on it. I act with that in the state G, and I just measure the mod square of that. This is just like measuring the norm of the state. And this thing is this guy. So this tells us that we can decover something like this with these. Okay, this kind of thing we have already talked about in the past, how to get this kind of stuff. Now, once we have something of this sort, and from whatever we discussed in the past, we can also find objects of this kind, then notice you can get the real part of the overlap of G with some basis state by just using an identity of this form. So equation 17 is just a identity in complex numbers. It's just equivalent to mod of z1 plus z2 squared. If you just compute that, you'll end up getting this. Since this is a real number, it becomes something very simple like this. Therefore, this fixes the real part of G's overlap with X. But it leaves a sign ambiguity for the imaginary part, because we know something like this, and this is equal to real square plus imaginary square. It will leave a sign ambiguity for the imaginary part. But for fixing the imaginary part, instead of using XR here, you can use XI, where XI was defined like this. And then you would be able to fix the imaginary part of G's overlap with X by using a similar complex identity of this form. Okay, great. So let me summarize this thing first. The first step in the entire procedure is to make a measurement of this kind, and this will fix the state's overlap with the basis vectors up to a phase. So you can have a set of basis vectors which are on the boundary, and the state's overlap with the basis vectors up to a phase can be fixed with a very simple measurement of this kind. But like I said, for getting the phase, we have to do a bit more work. The first part involves finding XR by trial and error. So XR is something that you have to just do it by trial and error, such that this is not equal to 0 and is a real number. And the overall normalization of the state G is chosen such that this equation is true. So G's overlap with XR is equal to really just mod of GXR. That's going to fix the overall normalization of the state G. Okay, and therefore we chose the fix. Therefore we have already chosen the phase of this guy, which will allow us to fix real part of GX from the formula which I described in the previous slide. And since this square is equal to the real square plus the imaginary square, we'll have a sign ambiguity in imaginary GX. And similarly, instead of using XR, we can just use XI. We can exactly fix this, thus completely fixing G of X for all the basis states. So we just need one XR and one XI, and that's good enough for fixing the overlap of G with all the basis states. Now, we again have a detailed procedure on how to find Xi using just the energy eigenstates in XR. We can of course discuss it, but it's just a very simple formula on how these two are related. So once you have XR and once you have the operators which create the energy eigenstates, you can just find Xi. Okay. So yeah, this is kind of a nice flowchart which summarizes everything. So the first step is that you check if G's overlap with the vacuum is 0. If it is not 0, you multiply with some unitary. In the talk I was using V acting on G, but in the paper we have written it with UZ acting on G. You act with some V of G such that the modified states overlap with the vacuum is 0. And then you have to find the reference operators XR and XI. Okay. Once you find the reference operator, using everything that I've told you in the last two slides, you can find the overlap of G with all the basis states. Once you have that, you can, transform the basis states, let's say, to the energy eigenstates if you want to. And then you can evaluate G's overlap with all energy eigenstates, where E is less than lambda. And then you ask if the estimated value of G is close to the real value, is close to the bulk operator, bulk state G, up to this tolerance factor delta. Okay, if this is not, then you have to repeat this thing with more accuracy. But if it is, then you're done. So this kind of summarizes how you can find G's overlap with all the basis states. Okay. Before describing two-point functions, if there are more questions on this, you can ask now.
How can we ensure that this protocol always works? Meaning, maybe we could have to do this protocol infinitely many times.
Yeah, so that, I mean, of course, that's, so in principle, of course, any quantum mechanical measurement will require infinite copies of some system. But in general, that has to be controlled by what accuracy you want to determine your state with. Okay, so here I'm fixing the accuracy up to some delta value. So this delta will tell you how much you need to do. But otherwise, yeah, there is a way to, kind of check if the estimated state is equal to the state G. We have it written down in our paper, which can tell you how you can exactly check this thing. It's just a few formulas, but I'm not sure if you're asking that. Are you asking that or something else?
I'm asking how can we ensure that we can get this protocol work in finite amount of operations?
So that's true for any quantum mechanical question, no?
Yeah.
In any kind of quantum mechanical measurement question, you'll always have that problem.
Yeah.
So yeah, so that's why you'll have to set some tolerance level up to which you want your answer to be.
Okay. Thank you.
Okay. Are there any more questions from protocol or?
Yes, sir.
Chandra, can I ask a question?
Of course. Yeah, Loga, please.
Yeah. So maybe this is perhaps related to the question that you just answered.
Yeah.
So, like, for example, many people have talked about trying to define some kind of complexity, within quantum field theory and so on and so forth. It's not always clear whether that makes sense. But I was just trying to understand in the context of this particular protocol that you guys are proposing, whether there is a natural sense in which you can define some notion of complexity, at least for quantum field theories within a in a sphere, in a box or something. This is slightly sideways to the main topic of the talk, but yeah, I was just wondering.
Actually, that's a great question, but I haven't thought of that at all. So I don't know if you can do that, but
I think we could. I mean,
Yeah.
the question is how many operations do we need to identify the state? I think we could. It would be. I mean, you'd have to define some measure on the set of states. So here we have some UV cutoff on the states. So then you could try and define the Haar measure for states below that, and then you could try and ask how many operations we would need to get to with some probability, with some high probability, determine the state with high accuracy. So I think one could try and answer that question. I mean, I don't want to give some estimate off the top of my head, but I think it's a question which could be answered in principle.
Okay, thanks.
Okay, all right. Okay, thank you for the question. Yeah. Okay, are there any more
Sorry,
questions?
Chandra, I had a
Yes.
I had a question.
Yes,
These,
yes, please.
a priori, these reference operators XR and XI have nothing to do with your X's, right?
No,
They're just
they
operators
have,
you're
yeah.
finding.
Yeah.
Is it guaranteed that you'll find some XR which has a which has this property that its overlap with G is a real number and so on?
Is it guaranteed or not? I mean,
as in, I guess I haven't.
So for XR, you just make a choice that XR
Yeah,
you can take
right.
any operator. Just take any operator, and
Uh-huh.
you just declare that x and g is a real number. We can do that because you're always allowed to rephase the state, overall state.
Exactly, yeah.
So you just take any operator
Right,
and
right,
get
right.
xt, and that's a real number. So
That's
then
right,
the only
yeah.
thing is you have to find something whose phase is only imaginary.
Right.
Once you have something which is only real and you have something else which has a complex overlap, you subtract off the real part, you'll get an operator which has only imaginary overlap. So, the first one is pretty easy to find because you just, you just declare it. You just take whatever your favorite operator and we call it XR. Because you can choose the overall phase of G.
Yeah, so that's essentially point 2 in here. So G's overlap with XR is chosen to be this guy.
I see. Okay, thanks.
Okay, great. So now let me talk about a complementary way of thinking about it. It's this way of thinking kind of illustrates on why, again, this won't work in something like QED a bit better. But let's say we are given some certain priors. Let's say I tell the observers that the state you have to determine is something of this form. It's some unitary acting on vacuum where the unitary is of this particular form. This F is some smearing operator, which is located near the center of ADS, and phi is some scalar field. Then the claim is that if you make a measurement of this kind, just G and HO, then you can get back the function F. H is, again, the total Hamiltonian, which lives on the boundary, and O is the boundary value of the scalar field. Okay. This, you can again write this particular thing down in a more physical way, which is just by measuring the expectation value of H in the state G modified, which is defined in this manner. And you can see that will give you this, and then by some formal arguments, you can again reconstruct F. Okay, so this is how it might work in gravity if you're told that the state is of this form. However, in QED, you might run into some trouble. That's because I tell you some state G exists, and which you're going to determine. And the state G is again of a similar form. It can be integral F with some phi plus phi dagger. I've just put phi plus phi dagger here to make it real. But yeah, in principle, some combination like that. Then you can consider, instead of G, you can consider something like G prime, which is F squared, which is, e power I integral f of x, capital F squared G. F of x is again a smearing function. And this is a gauge invariant operator now. So what it means is that it will commute with everything on the boundary. Since it's a gauge invariant operator, by microcausality, it will commute with stuff on the boundary. Therefore, by computing some 2-point function of the thing I showed you previously, you might not be able to determine this. Okay, but this way of thinking about it runs into a trouble. I mean, it's not a big trouble. It's just that it's hard to distill information. In principle, you can see you have all information, but let's say I give you very complicated states, then with a lot of smearing functions here and there, then following a procedure like this where you evaluate some 2-point function, 4-point function, or something, it just gets hard to recover all the functions properly. Therefore, it's more useful to think of a physical picture like we talked about in the previous slides. But if one is told that the state is a simple prior, something like this, then yeah, it might be worth doing it. Okay.
Can you please, if you don't mind, move to the previous slide?
This one?
Yeah. And then considering the, if it doesn't bother, can you please explain the third point again? I'm very sorry for the trouble.
So all I'm saying is that you evaluate something like this, and you just expand G mod again as 1 plus I lambda O, and G as 1 plus I integral fx phi x, and this is just equal to this. Now this is a 2-point function, and in order to exactly recover F, there's some formal argument which you can use by saying that these are separated by some small time widths, and you can make some series expansion in that small time width, and also on the left hand side, and then you can recover moments of F. So it's kind of a formal way of recovering F, but not an exact way.
Okay, so we are trying to recover the states using correlation function and the smearing function, which is determined up to order lambda.
No, you have to recover the smearing function, not So in here, I'm telling you that, let's say somebody tells the observers that the state is of this form, something like e power I fx phi x acting on the vacuum. And the goal is to recover f. F is ensuring that this object is centered around the vacuum. It's peaked around, not the vacuum, sorry. It's peaked around the center of ADS. So yeah.
What does that mean?
That just means you consider a graph like, something like a Gaussian, e power minus x square that's peaked around x equal to 0.
Okay.
Something like that. Okay.
Thanks.
Okay, great. So let me conclude my major points, and then if someone is interested in about more details of any of the things that I've talked, especially finding an explicit basis state or fixing xi's given that you know xr, and then orthogonalizing unitaries, we can of course discuss this afterwards. So as I said in this talk in the paper, the main point is that we demonstrated a physical protocol through which the observers near a boundary can access complete information about a pure state in the bulk. Okay. If such a protocol could be, if such a protocol can also be extended for a black hole, then it seems to suggest that all information that is contained inside a black hole is located at a single time slit on the boundary. But like I said, this strongly relies on something like if. As of now, we don't have a working protocol which works with the black holes for various reasons, but okay, we can discuss that. And now there are some conjectures about there being no global symmetries in gravity. However, if you did consider two states which only differed by a global transformation, then we have a similar set of ideas which you can use in order to tell, in order to discern which two states they are. And right now, everything that I've said is only in ADS, but it will be really interesting to see how to make a similar thing work in flat space. So in flat space, you've got additional complications, of course, super translation charges and other things, but we don't know how to bypass that in the present setting. So yeah, it will be interesting if we could do that. Yeah, thank you. I'd like to conclude here.
All right, thanks, Chandra, for that nice talk. Maybe we can unmute ourselves and clap for Chandra. And maybe we can move to more questions.
Yeah.
Hi, so I didn't catch this. Did you say you can distinguish between states only of the ansatz you mentioned, the prior you mentioned, or is it that you can distinguish between general states?
No, we can do it for any general given state as long as it's a pure state right now. Yeah. The 2-point function thing was, just to tell you how you might think finite point correlation functions are containing all information. Like finite point correlation functions in a single time slice, how that contains information about states in the bulk. But in principle, yeah, the protocol doesn't really need to use something of that sort.
Hello.
Yeah.
So Chandra, this is probably related to this statement of whether this can be extended to black holes and so on.
Yeah.
But can I ask a question? Whether do you have a way of distinguishing between a pure state and a mixed state? Because if I understand right, the whole protocol relies on an assumption that it is a pure state. Like you're not trying to determine whether, let's say if I hand you a state, you're not trying to determine whether it's a pure state or mixed state, but you're assuming it's a pure state, and then you're trying to determine it. Right. Is that right?
Yes, that's right. Yeah.
So if I don't assume it, if I just hand you a general state, which could also be a mixed state, how much of what you're saying will go through?
Well, I would think that if you have a mixed state, then you need to make much more finer measurements of this sort. yeah, that's one problem that I'm seeing. Like, other than that,
So I think for a mixed
yeah,
state, you'll need also POVMs. Like here we are only doing unitary operations followed by projective measurements. So if you have a mixed state, you should allow us like the mixed state operations also. So you should allow us like a Lindblad evolution of the state. So I think then we could generalize our protocol, and it would work also for mixed states. I mean, it's would be more complicated, but here we are doing pure state operations, unitary operations and one measurement. You allow us like Lindblad evolution, then I think we'll also do a mixed state. But we didn't want to go into that because then you can start asking, okay, what is it entangled with and so on. But I think in principle it's you generalize the powers of the observer and it'll work for mixed state also. I mean, we haven't done it in detail, but I expect it should work.
Sorry, Subrat, I'm just trying to understand your statement. So at this point, we are just talking about a unitary quantum field theory, and I'm giving a mixed state and a unitary quantum field theory.
Yes.
So what is your statement about Lindblad evolution? Not quite.
So if you have a mixed state, you see the observers should also be allowed to do a Lindblad evolution of the state, because they should be allowed to use ancillary qubits as well.
So you would take the just to make sure I'm following what you're saying. So you would take the unitary quantum field theory and couple it to some other system, and so to make it an open system, and then you're allowing that kind of operations also.
Correct, because the mixed state initially was prepared with that kind of an operation, right? Otherwise, it could not have been prepared. You entangled it, so you had to have turned on a coupling with some other system.
Sure. Okay.
I mean, these things are allowed in general when you consider like when you consider like local operations and classical communication. You allow these things in quantum information discussions, which is you allow the observer to use ancillary bits. So it's like this is actually not even, you don't even have to couple it. You can just do like you can do unitary operation, then make a classical communication, and after that depending on the result of that, do another unitary operation and so on. So you don't even have to think in some detail about dynamics. It's just that you should be allowed more general possibilities of measurement. So I mean, if you're allowed to do that, I think you could determine also mixed states. Actually, we haven't thought in great detail about the mixed state thing, but I should say that this is my expectation, that you should be able to also work out mixed states without difficulty in this situation. By doing these more general things.
And just one more question, and then I'll be done. Why don't you need such things in this for pure states? Like, and why do you need it only for mixed? I'm trying to kind of understand why only mixed states need such things, more things than pure states.
Let's see. Is there a clear answer to that? I mean, in general, I know the space I was thinking just that the space you're dealing with is a larger space, so you should allow it's kind of goes hand in hand, that if you allow like mixed states, you allow operations on mixed states, which are in general operations on density matrices. Rather than just doing unitary things. I mean, there's some technical point here actually, which is that I could try and explain. If you had just some arbitrary density matrix, I think if you just take unitary operations, I mean, I remember thinking about this at some point. There's some difficulty in recovering one of the elements of the density matrix, which is fixed by the fact that it's pure. I don't have a better answer to that more than the fact that if you have a mixed state, you should allow mixed state operations. You should allow like more than unitary operations. You should allow like you should allow me to mix the state some more, like with ancillary qubits and so on.
Yeah. So my question was that why don't you guys need this here?
Why don't we don't need it, but why don't we need it here? If you have a pure state, you can often determine what a pure state is. Much more simply, right? Because I don't know. Like, you know, it's like some extreme state in the space of all states. So that gives you a little bit of help. I mean, here it was because you could, you know, because you could look at the overlap of this. You could look at the mod square of the overlap of the state with different vectors, and that was enough to give you I don't know if I don't have a completely clear answer to your question of why we don't need it, but roughly speaking, these unitary operations and projective measurements already give you the mod square of the overlap of the state with a whole bunch of vectors, and that's sufficient to identify a pure state, but it's not quite sufficient to identify a mixed state, I think. But I don't have something much better to say.
Okay, thanks.
Okay. Yeah, if there are more questions, you can ask them now. Okay, yeah.
I don't have a question, but I was wondering if there are no more questions, maybe you can go a bit into this description of how you find XRs and XIs and this basis on the boundary and so on.
Yeah, sure. We can do that. Yeah. Let's see.
But maybe you want to wait a bit for questions. That's also fine. Whatever you want to do.
Sure. I mean, okay. Let's maybe wait for a few more seconds if nobody says anything. Then.
Cool.
Hi, Chandra. Is there a version of this story for, like, say, Euclidean black holes? Like, you have a small arc of the cigar, and just by so I guess it's about how these analytical arguments continue to Euclidean signatures, right?
Yeah. I'm a bit confused about what you mean by Euclidean black hole. Like, are you?
I mean Euclidean geometries. I mean, yeah. Sorry. So let's say I have okay. Let me take a Euclidean black hole because, like, just a cigar geometry or something. Would you say just by looking at, so then there is no problem of it seems like a Euclidean manifold where you can still find describe the quantum mechanics by path integral or something. And then would you say, like, just by looking at a small arc of the time circle, you can figure out what's the distribution in the whole manifold or something? I don't know if what I'm asking makes sense also. I mean, you can correct me.
I don't think I completely understand the scenario. Like, do you want to consider? Yeah, like, are you considering some excitation in?
Yeah, it's considering excitations in some Euclidean manifold and say Euclidean ADS. And would you say you can just look at by calculating correlators at the boundary, you can extend this protocol there?
I think. Right. So, I mean, I'm not completely sure I understand, but you will probably need to be given a bit more information about which particular microstate you're exciting, you're creating that excitation on or something in such a context. But yeah, I don't think I have anything more to say about that.
Okay.
Can I make a comment in the question? There will be an issue of state dependence, I guess, to describe operators in the interior of black hole, Euclidean black hole.
Yeah, but I don't think I'm not exactly sure what would come in. Yeah, maybe we can discuss this later. Okay, so.
Yeah, thanks.
Okay, so if there are no more questions, let me just try and tell you what how you can fix xi given that you need xr. So right, so this is a bit messy, but anyways, what you need to do for something like that is you need to just construct operators xe and iye. I guess the notations are very similar to the past, but these operators are just going to create some energy eigenstate for you. Okay, so in general, of course, if you act on the vacuum with a dagger, then you can get the first excited state, and then you can write the vacuum as phi plus I pi or something. Sorry, you can write a dagger as phi plus I pi or something like that. And you can think of these guys as analogs of those. So yeah, well, now again, you'll be using some very similar measurements like we have discussed in the past. Like you can act on the state G with such unitaries, and then you can get these kind of information. And okay, I'm not going into the complete description, but let me just tell you how you would construct xi, given that you know the real part of whatever's creating the energy eigenstate. So xi is just, you can just write down xi as this particular formula. So once you know xr, you can just find xi as this particular expression. And you can check that the imaginary part, you can check that the real part of this is 0. Therefore, it's by real part of this, I mean the real part of this and the overlap of this and the state G is 0. So this is a pure imaginary number. And yeah. And in order to get stuff like this, you'll have to make similar manipulations, which we've discussed in the past, and it's also there in the table. But yeah.
Sorry, here the XE is just the X's that you had earlier, these basis states, and then you are
not exactly. You can think of them as combinations of those guys. You can think of them as combinations of those guys, right? Which would create the energy eigenstate for you.
Okay. Right.
And the L's are just quantum numbers, like the angular quantum numbers, for example. Just have that. Okay.
So what has happened?
Sorry, I think I lost internet for a bit or something.
You lost internet, or Chandramouli lost internet?
Oh, I thought I did, but maybe Chandramouli did.
Hello.
Okay, yeah, we can hear you now.
Okay, yes. Actually, I think my internet went off, so I have to. Yeah.
Okay. So coming to this question that I guess Loga brought up earlier of the complexity, I guess that's one question to one thing to know is how complex these operators are, right? These XRs and XIs.
That's right. I mean, and as far as I understand, complexity usually tells you like, what all operations you need to do in order to go from an initial state to a final state.
Right.
So
it's
right.
So in some sense, these XRs and XIs have to be the simplest such operators that you can use. And then you can ask how many times do I need to use this protocol that you've detailed and be able to estimate the state.
Right. So, I mean, okay, XR and XI, as I said, you just need to use one particular XR and XI. So that's fine. And then, of course, you have to check the overlap of G with all possible basis states. Now, I suspect that step might be a little so-called complex because you'll have to check it for every possible basis state, right?
Mm-hmm.
Yeah, that. But of course, in the end, of course, you need to do it in an efficient manner such that you minimize complexity. So, it might be better to just check, the overlap of G with the energy eigenstates directly, or something like that. Like you would expect that energy eigenstates are, kind of G has an overlap with, let's say, the first few energy eigenstates. Like I'm actually just thinking out loud. Sorry, I don't have a very precise answer on how to minimize complexity in this case.
Okay.
But, yeah, we can talk more about it. Yeah.
Sure.
Okay.
Just one last question.
Yeah.
Could you make some comments on why this protocol is difficult for black holes?
Well, for black hole, discerning exactly which microstate is coming in would be really hard. In general, you might have to use higher energy eigenstates for that. So if somebody told you that the excitation is let's say state G is excited on top of a particular microstate, if somebody told you that beforehand and told you which about which microstate you're considering a small excitation, then possibly a similar protocol would work. But if somebody did not give you that bit of information and just told you that it can have the average energy of G is some value, then it might be slightly harder because you don't exactly know which microstate, about which microstate you're exciting stuff.
Yeah. Thank you.
Okay, so Sid, maybe if there are no more questions, then
yeah, maybe we can wait for a little bit, and if there are no more questions, then we can let you go.
Okay. No.
All right. Okay. Are there any other questions for Chandra? Okay. If not, let's thank Chandra again for this nice talk, and let's stop the talk right here. Okay. Thanks. Thank you, Chandra.
Okay. Thank you.